The equivalent dose. The effect that radiation has on human tissue depends on the absorbed dose and the type of radiation, whether it is alpha, beta or gamma, which that part of the body absorbs. This equivalent dose is a better indicator of the harm to the body by the radiation than the absorbed dose tells us. This is achieved by multiplying the absorbed dose with a special number, depending on the type of radiation, and this number is called the radiation weighting factor. So the equivalent dose is measured in sieverts, named after another famous scientist who studied radiation effect on humans, Rolf Sievert, and his name is given to the unit of equivalent dose, sievert, SV. So we take the absorbed dose, measured in grey, and we multiply it by the radiation weighting factor, measured in WR, and we then get what we call the equivalent dose. The radiation weighting factor, W subscript small r. The radiation weighting factor gives an indication of how harmful that particular radiation is if it's absorbed by human tissue. They are recorded in a table like the one shown on the right here. Alpha, beta, fast neutrons, gamma, slow neutrons and X-rays are all types of radiation and they're given the appropriate radiation weighting factor. You'll notice that alpha particles have the highest radiation weighting factor because of its high ionization capabilities. Remember, ionization can damage the cells and damage the cell's structure, so therefore it's very harmful. So the bigger the radiation weighting factor, the more harmful that radiation is to a tissue if that tissue absorbs that radiation. You can see alpha particles have got a radiation weighting factor of 20 compared to fast neutrons. They've got a radiation weighting factor of 10. So we would say that alpha particles are twice as much harmful than fast neutrons if they're absorbed by a piece of tissue. Let's see what happens when we calculate the dose equivalent. Let's imagine we've got a human liver and it receives an absorbed dose of 5 milligrays of fast neutrons, and simultaneously it's also going to receive a dose of 5 milligrays of X-rays. Now our job is to work out the total dose equivalent which that human liver received. So we have to consult our table and we have to carry out our little calculation, and the calculation is as follows. The dose equivalent, which we know is H, is equal to the absorbed dose multiplied by the radiation weighting factor. And we'll do it for the X-rays first of all. So H is going to equal to the absorbed dose, 5, and we'll keep the milligrays the way it is, and multiply it by the radiation weighting factor for X-rays, which we find according to the table is a value of 1. So we multiply by 1. So therefore we have the dose equivalents due to the X-rays as 5, keep the milli in, but the greys become sieverts. So there's our dose equivalent for the X-rays, 5 millisieverts. And we do the same thing for the absorbed dose of the fast neutrons. We have the dose equivalent H is equal to the absorbed dose times the radiation weighting factor. And that's going to be given us the following value. D is 5 milligrays, the absorbed dose is 5 milligrays, multiplied by this time the radiation weighting factor for the fast neutrons is 10. So we're going to have a dose equivalent of 50, and we'll keep in the same milli, and the greys turn into sieverts for the dose equivalent. So there's the two values for the dose equivalent. So in total we have the total dose equivalent, total H for that liver, is equal to just simply the sum of those two dose equivalents. So it's 5 millisieverts plus 50 millisieverts. That's going to give us a value of 55 millisieverts. So the total dose equivalent will be 55 millisieverts. The equivalent dose rate. It is more informative to know over what time the dose of radiation was received. I'll give you an example. You might say that you've eaten 26 kilograms of butter. Now, that's quite astounding, but you haven't told us the period of time in which you had eaten that butter. If you say you've eaten 26 kilograms of butter per year, then that gives us a better picture. Someone else says they've eaten 26 kilograms of butter over the past hour. then you begin to wonder. So when we state the dose equivalents of some radiation being absorbed by a person, it is better to know the rate of the absorption, how long the absorption took place over. And we can show that by that equation there. H with a dot above it represents the dose equivalent rate, and it's pronounced H dot, and it's usually sieverts per unit time. It could be sieverts per second, sieverts per year, or sieverts per hour. So H dot, the dose equivalent rate, is equal to the dose equivalent measured in sieverts divided by the time in which the dose equivalent took place on. Here's a wee example for you. A worker in a nuclear power station receives 0.02 millisieverts in a 10-hour shift. Determine the total equivalent dose received per hour during the shift. So we use our equation, and our equation is as follows. It's going to be H dots, that's the symbol for it, that's the dose equivalent rate, and that's equal to the dose equivalent divided by the time in which the dose equivalent was received. So that's going to equal to, in this case, 0.02 millisieverts. I'm going to divide that by the time it took to receive that dose equivalent, and that's 10 hours. So there we have our answer there, which is much more informative. 0.002. Keep the milli in, millisieverts, and it's going to be per hour. And that tells us a very, very important fact. It means that every hour that radiation worker received 0.002 millisieverts. So that's what we mean by the dose equivalent rate.